Hello students. You're welcome to today's chemistry lesson. We'll be studying symbols, formula and equations part 1. In our previous class, we learned that electrons move around the nucleus of an atom in fixed regions called shells or energy levels. These shells are arranged from the closest to the farthest away from the nucleus. And each shell can hold a maximum number of electrons, with the inner shells filling up first. We also discussed that the atomic number is the number of protons in the nucleus of an atom, and it determines the identity of the element. The mass number is the total number of protons and neutrons in the nucleus. Isotopes are atoms of the same element that have the same atomic number but different mass numbers, because they contain different numbers of neutrons. Finally, we noted that relative atomic masses are determined using the carbon-14 scale. This means the mass of other atoms is compared to the mass of the carbon-14 isotope, allowing scientists to calculate the relative atomic mass of each element. Our lesson objectives for today are to learn the chemical symbols of elements and their valencies, identify empirical and molecular formulae, and explain the law of conservation of mass. Chemical symbols are short codes that represent elements. Instead of writing long element names over and over, we use 1 or 2 letters to stand for each element. The first letter is always capitalized. If there is a second letter, it is usually a lowercase. These symbols come from the English names of the elements, like C for carbon, or their Latin names, like Na from natrium for sodium. This helps us express chemical ideas clearly, quickly, and correctly. Why chemical symbols are important? Chemical symbols make communication easy in science. They help us avoid writing long element names and give us a universal language that scientists everywhere understand. Symbols are also used in formula and equations, making chemical reactions simple to write and read. Let's connect the dots between these ideas. Valency simply tells us how an element combines with other elements. I want you to imagine valency as the number of hands an atom uses to hold onto another atom. Examples of valency explain using the hands analogy. Hydrogen has 1 electron in its outermost shell and needs 1 more to complete it, so it has 1 hand available for bonding, giving it a valency of 1. Oxygen has 6 electrons in its outermost shell and needs 2 more to reach it, so it has 2 bonding hands, giving it a valency of 2. Nitrogen has 5 electrons in its outermost shell and needs 3 more to complete the shell, so it uses 3 hands to bond, giving it a valency of 3. Carbon has 4 electrons in its outermost shell and needs 4 more to fill it up, so it stretches out 4 hands for bonding, giving it a valency of 4. Once you know an element's valency, you can predict how it will form compounds. So always remember, valency is the combining power of an element. An empirical formula is like the simplified version of a compound's formula. It shows the simplest whole number ratio of the different atoms present. Think of it like reducing a fraction. For example, the fraction 6/12 can be simplified to 1/2. The empirical formula works the same way. Let's look at these examples. Glucose. Its molecular formula is C6H12O6. All the numbers 6, 12, and 6 can be divided by 6. When we do that, we get the simplest ratio, 1 carbon, 2 hydrogens, and 1 oxygen. That gives us CH2O. Hydrogen peroxide, H2O2, also simplifies. Both numbers can be divided by 2, giving HO. Ethene, C2H4, follows the same idea. Divide everything by 2 and you get CH2. So remember, the empirical formula doesn't show the full structure or the exact number of atoms. It simply shows the simplest ratio that represents the compound. To help you remember, Think of an empirical formula, like a recipe ratio. For example, if a recipe needs 2 cups of rice and 1 cup of beans, the ratio is 2 to 1. Even if you cook more food, the ratio remains the same. In the same way, an empirical formula always shows the simplest ratio of elements in a compound. The molecular formula shows the actual number of atoms of each element present in one molecule of a compound. For example, the molecular formula of glucose is C6H12O6, which means that one molecule of glucose contains 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Another example is water H2O, which shows that one molecule of water contains 2 hydrogen atoms and 1 oxygen atom. The law of conservation of mass states that matter cannot be created or destroyed. This means the total mass you start with in a reaction must be the same as the total mass you end with. Atoms are only rearranged during a reaction. They do not appear or disappear. So chemical equations must be balanced to keep both sides equal. For example, when calcium carbonate breaks down, it forms calcium oxide and carbon dioxide. If you start with 100 grams of calcium carbonate, you get 56 grams of calcium oxide and 44 grams of carbon dioxide. The total is still 100 grams, showing that mass is conserved. Congratulations on completing this lesson. You should be proud of yourself. Let's check your understanding with a few quick questions to recap what you've learned. In this lesson, we learned about the chemical symbols of elements, which are represented using 1 or 2 letters, and their valencies, which describe the combining power an element needs to join with another element to form a compound. We also identified empirical and molecular formula, with the empirical formula being the simplest whole number ratio of the elements in a compound. In addition, we explained the law of conservation of mass, which states that matter can neither be created nor destroyed during a chemical reaction. In our next class, we will continue with symbols, formula, and equations, part 2. Thank you.